So if we want to find the volume of a solid, we can split it up into infinitely many small slices, and if these slices are thin enough, then we can approximate them as a cylinder. Now obviously this is already just a cylinder, but if the shape was irregular, then each slice would have a different area. And so the volume of each slice will be the cross-sectional area, which can differ from slice to slice, times the height or width, which is dx or dy, depending on which axis the cross-sections are perpendicular to. And so to find the volume of the whole solid, we just integrate the volumes of each slice. So we take the cross-sectional area times dx and integrate from a to b to find the volume of the solid. So the easiest solids to find the volumes of are solids of revolution, which is when you take a region. Here we have the area underneath this curve f of x, and we revolve it around a line. So you turn it, and the line is usually the x or y axis, but it can be any line. So you take this region and you turn it around the axis, and it makes a solid. And so in a solid of revolution, the cross sections are always cylinders, and so the cross-sectional areas are always circles. And you can see here the radius of this circle, when we revolve it around the x-axis, is just equal to f of x. It's the y value at any point will be the radius of this cross-section circle. And so the cross-sectional area will just be pi r squared, or pi f of x squared. And so then the volume of each of these slices is the area pi f of x squared times dx. And so for a solid of revolution around the x-axis, we just integrate from a to b of pi f of x squared dx. And this is called integration by disks. And well, you have to be careful because this is not always f of x. It's just whatever the radius of each cross-sectional circle is. So it depends on which line you revolve around. So we can use this to find the formula for a volume of a sphere of radius r. So we can draw a semicircle, and then if we revolve this region around the x-axis, we'll get a sphere. So this equation of a circle is x squared plus y squared equals the radius squared. So the equation of this semicircle is y equals square root r squared minus x squared. And so the cross-sectional circles will have a radius of y, which is this. And so we use our formula and plugging in the f of x, which is the radius in this case. And if we integrate, then we can find the volume will be 4/3 pi r cubed, which we already know is right. And so if we take the region between two curves and revolve that around a line, then we get a solid of revolution that has a hole in the middle of it. So you can see here we took the region between these two lines, f of x and g of x, and when we revolve them, we get a cylinder with the hollow tube in the middle. And so taking the cross-section circles, they'll have a hole in them. So the area of each of these cross-section circles will be the whole circle, which is the pi times the outer radius squared, minus the hollow part, which is pi the inner radius squared. So in this case, the outer radius would be f of x, and the inner radius would be g of x. So the cross-sectional area would be pi f of x squared minus pi g of x squared. So then the general formula, if we revolve around the x-axis, is the integral from a to b of pi times f of x squared minus g of x squared. And remember, this is just the outer radius squared minus the inner radius squared. It's only f of x and g of x if you revolve around the x-axis. And this is called the washer method. So let's say we have two curves, 1/2 plus x squared and y equals x. And we take the region between these two curves and revolve it around the x-axis. So here, the outer radius of each of these cross-section circles is the upper function, 1/2 plus x squared, and the inner radius is x. So we take the integral from 0 to 2, pi times the outer radius squared minus the inner radius squared. And doing the integration, we get the answer 69 pi over 10.